Hi there, this is Matt Heffernan and welcome back to my channel. Today we're going to be having another episode of Slithy Vlogs. I know we haven't had one of those in a while. We've been doing some other things that I haven't been put under the Slithy Vlogs umbrella, but still this is where I do more of the informal things, and this isn't as structured or perhaps with an eye towards developing a tutorial series like some of the other things. This is just hanging out and having fun. And if you've seen the most successful episodes of Slithy Vlogs, of course, those are the 8-bit battle royales. And so today we're going to do the 16-bit version of this. We're moving forward. I think I've taken the 8-bit battle royale about as far as it can go because we have a lot of real limitations with what you can do with these 8-bit machines and the different kinds of benchmarks you can run, and sticking to a Mandelbrot set plot on there. There's only so many different ways you can do it that are going to really tell you much of anything about the relative strength of and power of these different machines. So let's take a look at what we can do to move this fight into that 16-bit arena. But first, we need to really answer the question of what is 16-bit? Well, it's technology, of course. There's an actual technical thing that means 16-bit. But it's also kind of difficult to categorize any sort of individual technology as being quote-unquote 16-bit technology, because really that moniker of 16-bit is wrapped up in marketing. And what's really important is this is something that we're marketing as 16-bit or 8-bit or 32 or 64-bit or whatever. And I have a whole video about that. In fact, if you look up right now, I'm giving you a link to a video essay I have called On Bits and Branding. And I go into great depth on a lot of my interpretation of how we've used bit widths for marketing purposes and what it really means, and a lot of the implications of doing that, and basically what has happened to that in the years since, when we started talking about 16-bit as being a thing that was superior to 8-bit. And because of that moment, which started happening in the late 1980s, it's wrapped up in nostalgia. We have a certain sense of what 16-bit is because of that 16-bit revolution that was marketed towards us in the late 80s and early 90s. We have a certain nostalgia for that period and understanding of, well, this is 16-bit because it looks like this. And so we're going to go into each of these, first of all, to help nail down what we're going to do for the 16-bit Battle Royale. And of course, most importantly first is the technology. Now, here we have a extremely simplified version of what you could call a von Neumann computer architecture, where here on the left we have a processor. And the processor could be a microprocessor where everything is all integrated, but there could be parts of these components are split up into different discrete components that are wired together. But then you have some sort of memory that's attached to that. And within this architecture, you're going to be dealing with memory data and bringing that into the processor. And that data is going to be digital data. It's going to be ones and zeros. And however many ones and zeros are in that word that you pull out of memory, that's going to be the bit width of the external data bus. That's how big those, it could be a single byte, just 8 bits for 8-bit memory access, but it could be 16, 32, 64, or some sort of weird thing in between, like a digital signal processor could have a 24-bit data bus. And then, of course, there's the address bus. And even the most simple 8-bit computers don't have a mere 8-bit address bus, because that would only be 256 bytes of data. That's not a lot of, of the program or anything to deal with, and that you really need to have a wider address bus than your data bus. So most 8-bit computers have a 16-bit wide address bus, but of course we have the understanding that a 16-bit address bus is not going to make a computer 16-bit. It's absurd. It's just not going to happen. But then we get into the actual processor itself, and the memory management component of that processor is then going to relate all of this. This external data bus is going to get routed into the registers, and those registers are going to be a certain width. And then the data from those registers are going to be sent into the arithmetic logic unit, or ALU, and that's that big purple V thing. And that is going to do the different arithmetic and logic operations on pairs of register values. So you're going to have anything from adding and subtracting on the arithmetic side. To the logic end, you're doing bitwise ands and ors, all these different sort of operations that you can do on data. That's what the ALU does. So it's a very important part. It's really the key part of where the processor is doing the actual processing, and then the rest of it is just sort of moving the data around. And then the results of the operations that come out of the ALU go back onto that internal data bus that can then get fed back into the registers, or go back out through the memory management system and onto that external data bus again to be written off to memory, or to a port, or however the particular implementation of your system is. It's going to have ways of being able to get that data back out onto some external device. And so that's how everything works. So where do we draw the line? What do we say is what part of this whole architecture needs to be 16 bits for it to be a 16-bit processor? Well, like we've already said before, it's not the address bus. The 6502 and the Z80 both have 16-bit address buses, but they are certainly not 16-bit CPUs. And it's also not the registers, because again, with the Z80, it technically has 16-bit registers on there. And even the 6502, the program counter, is a 16-bit register on there. And a lot of other 8-bit computers have 16-bit registers, but they're not dealing with data in 16 bits in any other part. The external and internal data buses on all of those 8-bit processors are just 8 bits. But even the external data bus, we got to eliminate that, because there are 16-bit processors that have an 8-bit external data bus, like the 65C816, or even the 8088, which we're going to be actually covering in this video. Those had 8-bit external data buses, mainly because the components outside the CPU, in that era, they were made for other 8-bit computers. So to make a 16-bit computer with a 16-bit external data bus, that was a lot to ask. It was a lot harder to source parts for that, and just harder to build. So we just didn't do it. We used an 8088 or a 65816 and had a processor that was internally 16 bits, and then could interface with 8-bit data outside of the CPU. And so that's what we're going to look at, are CPUs that have an internal data bus that's 16 bits, and along for the ride is a 16-bit ALU, so it can do direct operations on 16-bit data. So you could have two 16-bit registers, and you're doing a 16-bit add, say, within that ALU. Because like you can see from the Z80 videos, yes, you do have 16-bit registers. You could add BC to HL and do a 16-bit addition in a single instruction. But that instruction is actually running through an ALU that's only 8 bits wide. And so it's actually doing 2 adds. And that's why it takes so long. If it was an actual 16-bit processor, it would just have to crank through that ALU one time instead of cranking through it twice and handling all the carries and all of that. You wouldn't have to do that if it were an actual 16-bit CPU. So those are the processors we're going to be looking at within the 16-bit Battle Royale. Stuff that can actually do 16-bit math internally to itself, even if it does have that external bottleneck of only 8 bits for its external data bus. And of course, the addressing can be pretty much anything at that point too. It could still just be 16-bit addressing, but most of these 16-bit processors are going to have even wider address buses, like 24 bits, even up to 32 bits, like the 68,000, the Motorola 68,000, which we'll be seeing in later episodes. That has a 32-bit has 32-bit addressing internally, but then like the address bus is not actually 32 bits wide. And the external data bus is definitely 16 bits because it's a 16-bit CPU on the inside, that original 68,000. So that's what we're going to be really talking about, is internal 16-bit technology. But that is going to conflict with some people's understanding, because for them, it's about the marketing. They were, especially if they're of a certain age, they will have had a 16-bit marketed to them. Or maybe if they're a little younger, they may not have had that, but they had the original 32-bit marketing, where it's like, hey, we got to upgrade to Windows NT or Windows 95, or a later version of the Mac OS, where it's now a proper 32-bit operating system. And even furthermore, going into 64-bit, that's a more of a recent development, where moving everything to 64-bit. But people will have that idea of what 16-bit was, because especially with the consoles, we would see the Genesis and the TurboGrafx 16. And of course, the Genesis was the Mega Drive, Sega's 16-bit console, and both of them playing up the fact that they were 16-bit machines, even though it's a little debatable with the TurboGrafx 16 that it's properly a 16-bit system. It's definitely a far cry from the 68,000 that was in the Genesis. And then later on, of course, the Super Nintendo, the Super NES, was compared to the original NES. That was an 8-bit machine, and the Super NES had that 65 C816 based processor in it, where again, it has on the outside a lot of 8-bit trappings, but on the inside it could really crunch hard on some 16-bit stuff and have a wider address space as well. So, but that marketing is still really important, and because that leads to then the nostalgia of especially the games that we'd see a game like Super Mario World or Defender of the Crown, and these were examples of games that were put forth saying that, hey, here the Super NES can play Super Mario World, and look how much better this is than Super Mario Brothers on the NES, or Defender of the Crown. Look how much better that is on the Amiga compared to, say, Ultima on the Commodore 64. That was your 8-bit computer, and now this brand new 16-bit computer, the Amiga, can play these more sophisticated games. And so a lot of this whole 8-bit, 16-bit thing gets tied up into that nostalgia because of the marketing, and then a certain idea of, well, what that's going to look like. Well, even though we're doing 16 bits in this Battle Royale, it's still going to look very much like the 8-bit Battle Royale, because we're doing trying to do more of an apples-to-apples comparison in terms of our initial attempt at generating a Mandelbrot set with BASIC. So let's take a look now how we would get to this point where we would have a 16-bit machine that would still do pretty much what those 8-bit machines would do, but why we're doing any of this to begin with. So if we take a look at when 16-bit became a thing, it's kind of weird, because a lot of the original computers were actually wider than 16 bits on their data bus, because 16 bits, you only go up to 65,536 if you're dealing with an unsigned value. If you're dealing with signed values, that's cut in half. It's a very coarse range of data, and the ALUs for enterprise systems like these big IBM mainframes, the early digital equipment mainframes, and all these other UNIVAC, all of these, 16 bits wasn't going to quite cut it. So a lot of these computers had wider registers than that. And not necessarily like a power of two. It wouldn't be like, well, they are 32-bit. No, there was some of them a lot of them were like in between 16 and 32. But what you did have was in the 70s, the dawn of the microprocessor era, which I talked about in my first Z80 video. And that we saw that the very first microprocessors, all on a single chip CPU, it started with 4-bit, but then 8-bit started taking over. And that's what became most popular for a microprocessor in that first generation of microprocessors. But then what we saw around the same time was, all right, that's fine if you have a microprocessor. Those are for embedded applications or little toy computers like the Apple One or something. It's not like a real computer, anybody's doing anything important with. If you had an important thing to do, you had what they would call a mini computer. And this was an affordable system where you could actually do serious work on. But it's a mini computer in so much that it, instead of taking up a whole room, it takes up just like a quarter of the room, like this DEC PDP-11. So it's pretty small, but the CPU of it is actually this component you see on the bottom, and it has like some tape drives above it and some other just sort of filler area between them, where it has some other components that are sort of hidden on the front end. And it didn't have a CPU. It had a discrete logic to build its central processing unit. It did not have a microprocessor. But it was an actual 16-bit system, and that's how they sort of were able to cut the cost, to cut the actual footprint that computer would take up. And with the 16-bit a mini computer, that's how things like Unix and the C language came about, is that these were systems that were, even though they were kind of cut down from these big mainframe systems, they were capable enough to have a modern, sophisticated operating system on them. But the microcomputers, they really couldn't do that, especially with just these simple 8-bit processors. And that's when these 16-bit microprocessors started becoming a thing. And it's like, well, okay, we're going to have to get that PDP-11 scale computer, that central processing unit, onto a single chip that we can crank these out a lot cheaper. And so the first one to really do this successfully was at National Semiconductor. They had their IMP-16, which came out in 1973. Now, nothing much ever came of this processor. It was really more of a prototype, just a proof of concept, saying that, yep, we can do it. We can do, on a single silicon die, a 16-bit microprocessor. And so, yeah, congratulations. What are you going to do with it? No, nothing. We're going to do nothing with it, pretty much. So eventually, a few years later, 1976, Texas Instruments came about and said, hey, we can make a microprocessor, and we can actually make it do stuff. And we're going to call it the TMS 9900. And that came out in 1976. And eventually that would be the processor that is the basis of actual 16-bit microcomputers that would hit the market. But it would still take a few years. And in the meantime, the folks back in California at Intel, they had already had success with the 8008 and the 8080 processors that were showing up in these early homebrew computers. And now they said, all right, well, we're kind of losing that 8-bit market to Zilog. The Z80 is taking off. It's becoming the standard. It has additional features. You know what? We're going to become the new standard bearers for 16-bit. And of course, as you know, they were fairly successful in that. And their first attempt at that was the 8086. And that came out in 1978. And that was fully 16-bit across the board. It had a 16-bit external data bus, unlike the 8088, which came later that had the 8-bit external data bus. But the 8086 itself did not see as much market adoption as the 8088 because, again, building a computer around it, you got to have some off-the-shelf parts that are going to make it a lot easier. And so we're going to see exactly how that went down. So let's move ahead a bit to 1979. So what happened? Well, the folks at Texas Instruments, they put out the TI 99-4. And that was really the first mass-produced 16-bit microcomputer that a major manufacturer was putting out, and they were getting it into stores and selling it for a price that was a lot cheaper than, say, a PDP-11. But it was still in 1979 dollars, over $1,000 to get. So it was certainly not cheap. It was not like a casual expense for a home computer. And the reality is that what this guy did was no better than that. And in 1979, for half the price, you could get an Atari 800, which was a vastly superior computer. So it's like, well, who cares if it's 16-bit? This is a piece of garbage. Why would I want this? And there was nothing good about it. Bad keyboard. It just had like little calculator style chiclet buttons on it. There was almost no software that came out for it, unlike, say, the Atari 800, which had all sorts of games, and then the Apple II and the TRS-80 were all gaining speed. The Tandy color computer was about to come out. All these systems were coming out with all sorts of software, but not so much for the TI 99-4. And ultimately, through 1981, these first couple years on the market, they only sold about 20,000 of them. It was way overpriced and way underpowered, and it didn't have a reason to exist. So 8-bit computers continued to dominate the personal computer market up until we got to 1981, and that's really the watershed year. So what happened first? Well, TI came around and said, all right, we're going to have a new 16-bit computer. It's still going to be based on that same processor. It's the TI 99-4A. And what this guy is going to be is a heck of a lot cheaper. We're going to get the price down to $525, still a bit overpriced, but it's going to start approaching the price point that's appropriate for the technology, and we're going to add in the capability to make it a much more usable system, be able to interface with tape drives and disk drives. It's not just going to be a cartridge-based toy that you can do nothing with. And it started doing really well once they got that price down further and further, and eventually down to $99. So that when it went off the market in March 1984, of course, the Commodore 64 completely ate its lunch once it got down to like $200 or $300. And of course, the VIC-20 was also operating in that same price point at that time. And yeah, basically TI never made any money from these extremely early 16-bit computers. They were losing money on each one. They were doing all sorts of marketing gimmicks and even doing rebates, trying to get people to buy. It's like, here, you buy this computer for $300 and we'll give you a $100 rebate. Basically, that was just a $100 bribe to buy something because they still weren't making money on that computer at the $300 price point. So it was a giant boondoggle for TI. The processor, that TMS 9900, never really went anywhere. But IBM knew what to do. They had kind of gotten into the personal computer market earlier. They had a system called the 5100 that was sort of like a poison pill into the personal computer market. It was meant to be a true portable. It had like a built-in display, and it's like, well, no, it's it didn't turn out well for them, and it didn't dissuade the rest of the country from going and buying these cheap 8-bit micros that were out there. So they said, all right, well, we're going to make one based on the 8088 because it's that 8-bit external data bus. We can make it very inexpensive, off-the-shelf parts, and it's pretty much an open platform that we're going to design a computer around. And you could get the most bare bones one for only $1,565. So a little bit more than that original TI 994, and just vastly, like infinitely more capable than that. But of course, for that low price, you didn't get a whole lot because you got the very bare minimum computer, only 16K of RAM, just like the TI 994A, but a monochrome display adapter, no color graphics like that TI 99, and no floppy disks even built in. You would just have had a tape component. But in reality, nobody bought this base model. Most computer users, if they were going to invest in IBM PC in this very first generation, they were at least going to get one floppy drive on that. And I think also a lot of them would opt for for more memory in it. And also what came out at the same time was the optional CGA, the color graphics adapter, which you could put in there and connect that up to a composite or an RGB monitor and be able to get color graphics. And again, the colors not as impressive as even what the TI 994A gave you, but the color graphic games were not what the IBM PC was built for. It was built to be a real useful personal computer that you could do serious business on, that a small business could take, where being able to have their own mainframe or even time sharing on a mainframe was not really going to work for them. But they could shell out a few grand for each PC and put them on a few desks, and that was all the computing they would need for the short term. And of course, as you know, we're still living with the descendants of this 5150. The computer, unless you're watching this on a phone or a tablet or something like that, if you're watching this video on a PC, chances are it is a descendant of this very computer and just an evolution from this original architecture. So let's take a look now at what those 8-bit computers from the same time period were able to do. Well, of course, the Commander X16 is not from this time period. It's a modern version of a Commodore 8-bit computer. So it could do it very quickly, 23 seconds. And that's not really fair to compare it to the vintage 8-bit system. So the fastest among those was the BBC Micro, which has a 2 megahertz 6502, very, very efficient and fast, and was able to do this Mandelbrot plot set for a mere 1 minute and 37 seconds. Very, very fast. What we're able to do now is see if these 16-bit computers can do it any faster. What we have as our absolute baseline for basic is the Sinclair ZX Spectrum, which it took a full 4 minutes and 33 seconds to do this plot. So could the 16-bit power of the TI 994A do better than the Sinclair ZX Spectrum? It was certainly a more expensive machine. At least initially, it was quite a bit more expensive. And it came out, but it did come out a year earlier. And eventually, though, it would have been at about the same price point for a lot of its existence, especially towards the tail end. So how does it actually stack up? So some folks again may be surprised, even if they had one of these TI computers, that it is a 16-bit computer, because it definitely looks and feels like an 8-bit computer of the time, and it has about that same level of capability. And like all those 8-bit computers, pretty much what it had, if you didn't have a cartridge stuck in, was this TI Basic that was built in. So what I can do is go into the Basic. If you had a cartridge for an extended version of Basic that was optional, you could put that in there and select that at that initial menu. But here we're just going to do it with the built-in bog standard TI Basic. And how is it going to be able to handle the plot? And the truth is, actually, with the extended, it's not any faster. It just has additional features that we're not taking use of and that wouldn't really help us at all. So let's take a look. How are we going to get this computer to do the same plot as these other ones? Now, as a bit of review, here's the Commander X16 version. Commander X16 is pretty simple, and a lot of this code is still reusable on the TI-99. And here we can see our Y range is going from 0 to 22, and our X range from 0 to 31. So we're going to have a 32 by 22 bitmap, effectively, that we're plotting for a Mandelbrot set. And so yeah, here we can take this code, and to make it work for the TI, we got to do a few things differently. So you can see here, first of all, it's a lot more code. That we're finally getting to the beginning here at line 100. This is where we actually see back here this same line 100. But instead of just saying, hey, screen 0 and we're ready to go, now we've got to do things a little, we got to do a little bit of setting up, because it's kind of weird the way the TI works for color. Here we can see at the beginning, we are getting the screen set up, saying, all right, we're going to be doing like basic text graphics here, and then we're going to clear the screen, and then what we need to do is set up the palette that we're going to be dealing with the text. And even though there are about 15, like the ZX Spectrum, there's 15 different colors that are available for the TI-99 4A, but you can only have 12 different colors on screen at a time without doing some sort of weird timing thing. So what we're going to do is go ahead and select those 12 colors, which is what we do here with this for loop. And we're just selecting colors 2 through 13. Then picking up this array here, these 15 different colors, and we're actually going to have to identify the colors based on the character codes. And you can see here, like 32, that's the color code, the character code for a space, and that's going to end up being black. But then these other ones are going to have different background colors. Now, if we use these, I had picked these particular characters out because they don't have a lot of pixels to them, and mostly the background color could shine through, because then in this loop right here, I am then just go ahead and I just remove all of those pixels from the character, because up here I've just been setting the background color to this I+1, and that's how we've set up the set up the palette. So it's all going to work out that these different parts of the character set are going to have colors permanently assigned to them. It is kind of weird, and so the space is only on that one set, and we come back to that at the beginning and the end. And then we do have a couple of reused colors here. We can see the 67 and 73 do make an appearance again, because we had to repeat 3 of the colors in order to get 15 different colors for the 15 different iteration counts that we're going to see in the code. So it doesn't matter too much, because where most of the plot is going to take up these colors, and then we're going to get to black again at the end once we get to that sort of infinite depth part of the plot. And so let's see what this actually looks like. Well, we can copy this and then go into our emulator and we can paste it in there. Now this emulator, I've done a lot of testing. This is cycle accurate. It's called Classic 99. It runs on, it's made for Windows, but on Wine it times out exactly the same. So what we're going to do is, now that we have this code in there, we're going to go ahead and run it. But first I'm going to have my stopwatch ready, and I'm going to type run and get it going, and we're going to see this plot happen right now. So you can see a bit of a delayed response before we get to some non-black part of the plot, but it's okay. And we can see here it's still mostly those first few colors that we selected, but it is definitely not going quickly. This is the easy part. This first line, that's the part that most of these computers get through almost instantly, but it is chugging through this math and having a heck of a time. So we're just going to sit back and watch this, although of course I'm going to speed it up for you so you don't have to sit and wait through the whole thing. So here we go. See, here we're about the halfway point. Yeah, there it is. There's the little nubbin there on that end of the cardioid, and we're already at over 3 minutes. So yeah, this is not going to be a fast performance. We're coming down the end of the pike here. Let's go. All right. 6 minutes and almost 5 seconds. And in fact, I'll be kind, since it was 6:04.99. Maybe I was a few milliseconds too slow on that, so we'll call it 6:04. So yeah, not too great, considering at just over 4.5 minutes, even the Spectrum was able to generate this plot. But I tell you though, compared to the Spectrum, this color palette looks really nice. I really enjoy the color selection that TI came up with this. It's just bright and cheery, but not garish. It's a really nice looking palette. So let's take a quick look before we move on at what this would look like if we if we didn't do this bit of code over here, where we are basically clearing out all of these characters, these character codes that would have normally non-space characters, and just turn them into spaces so that we get these nice solid blocks on there. Well, the easiest way to do that, well, let me first reset this. And here I'll do another one. And we're going to repaste this code in here. And then what we're going to do is just do 75 and enter. And that'll get rid of line 75. And so now we're no longer changing these characters. And it is nice with the TI that you can change any character on there. If you don't like ASCII, you don't need to have ASCII. And it also is nice that it is pretty much a straight up ASCII character code, the character set. So it works out pretty nicely. So let's go ahead and run it now, and we'll see what it looks like. So of course we're going to black, and then the black squares are black, but now here you see the non-squares, the non-black squares have these random seeming characters. Well, these are characters that I specifically chose to not have too many set pixels within them, and that's works out well enough if you didn't want to go through that little other for loop, but you go through it pretty quickly. This doesn't really add to the performance significantly. It's that one-time shot of changing all these characters to be blanks. But this also at least gives an illustration that, yeah, in order to do these different colors, we have to use different characters to print out to get different colors. We can't just say, all right, this character is going to be this color. No, basically, whatever color you have for that character, you are stuck with that color. And then you change that color for the character. It'll change all the instances of not only that character, but all the other characters from its little group. So, yeah, it's kind of a difficult and weird way of doing things. But if you knew that, hey, I'm going to have a background and foreground color for each group of characters, and so it's like, hey, I'm going to have only 8 different ways of using these two colors together, and that's fine. That'll work out. And then if I'm using a different pair of colors for a tile, I have a whole nother set of characters that I can overwrite with custom tiles. So you can see why, even though it's so vastly underpowered, that you could still make some decent games with it. It would be interesting enough to make and easy enough to make, even though on the basic is really slow. If you did have the ability to do the assembly language development for it, you could probably do some interesting things. But you'd still run into the problem that there were pretty much no other computers that used this same processor. This was pretty much a showcase for that TMS 9900, and it wasn't like you could take those skills as a TMS 9900 developer and then go use it at a whole bunch of different companies. It was pretty much only good for TI and for this particular processor. And TI had other processors too. So yeah, it wasn't like, hey, if you were a Z80 or a 6502 developer, then hey, you could move around and make do programming for all sorts of different platforms and specialize in that. It's definitely, they did not do themselves any favors in the market. And this was just a big money-losing boondoggle for Texas Instruments. But, they turned out all right. TI is still doing just fine, making all sorts of little chips for all sorts of weird things. So, anyway, that's it for the TI. Let's move on now to Big Blue. So, in order to do any sort of PC emulation, now, it's not really emulation because I'm running on a PC. This is still an Intel x86 processor, although it's a Core i7, not an 8088, and it's going to be a little difficult that I could still run that same instruction set architecture for that original IBM PC on this machine. Even though it is a modern 64-bit processor and it has that whole separate instruction set. But to get a execution environment on pretty much any system, it doesn't even have to be an x86-based system. You can use DOSBox. But first you need to kind of set it up in just the right way. So what we're going to take a look at here before we run DOSBox is the configuration file. And you can see, if I go down to cycles, you can say, all right, well, I'm going to emulate we're going to say how many instructions I can try to emulate in each millisecond. And what we can do is say, all right, based on our current speed, I can do, say, 250 instructions per second, and that's going to get me pretty darn close to a 4.77 megahertz 8088 processor running on the original IBM PC. And then, of course, later the PC XT had the same processor running at the same speed. So so 5150 or 5160, the performance is going to be pretty much exactly the same. So let's take a look at how that's going to run. So if I do DOSBox, my modern Linux computer turns into a DOS computer. Look at this. I got a DOS prompt on my modern Linux computer. It's great. So what I first need to do now, unlike, say, the TI-994A, the IBM PC was a bit different. If you were going to run BASIC, you had a few different options. Now, if you just had that really standard, even without a hard drive PC like about 5 people actually had. Most people would opt for the disk. You had the built-in cassette basic that came on a ROM in the original IBM PC. But if you had a floppy drive, then you could run the advanced basic, the basic A as it was called, and that worked great if you had an IBM PC. Well, DOSBox is not really fully emulating that original IBM PC. It does not have that same BIOS, and so it's not going to work exactly the same. So there's going to be compatibility issues with certain software that really required that all that IBM ROM, that IBM cassette basic, to still be there, available in ROM. And of course, Microsoft, the company that actually created that basic interpreter, like they did for most 8-bit computers and 16-bit computers, is they said, well, we'll, for a clone, we'll just take the cassette basic in the ROM and that advanced basic that was on a floppy disk and just put it into one package that you don't need to have that ROM there anymore. It's all coming off the floppy disk. So what we're going to do is virtually put that floppy disk into our DOS box. So we're going to say mount A, and then I can just give it my actual Linux directory here. And I have a little tools directory, and I have in there a little DOS floppy effectively on there. And now if I go to A, there it is, and I have GW Basic. And then I have a basic program that I have saved in that tokenized basic format. And we're going to take a look at that in the basic interpreter. But first, we're going to take a look here at this other program called MIPS. Now, if I run MIPS, what this is a benchmark program for PCs. And it was made specifically for emulation. So it's like, here, how am I going to get my particular DOS box, VM, whatever I have, running as close as I can to specific PCs and clones? And so here, what I've done by doing that cycle count to 250, I see here I have an overall performance of about 1.02 times the speed of that original IBM PC. I'm going to call that close enough. As you can see, there's a separate different benchmark for the IBM AT, which of course had a 8286 running at 8 megahertz. And as you can see here, it's actually, even though it's less than twice the clock speed, the 286 is a lot faster in general, and it's effectively 4 times faster than that 4.7 megahertz 8088. So without further ado, let's bring up GW Basic. Again, same as the IBM Basic A, but this works on clones, and DOSBox is effectively a clone. So we're dealing with now an IBM PC/XT clone at this point in terms of our speed and performance. So we can load up this thing I call man CGA. So I created a basic program, just like the last one we saw, that is made to run on a CGA-equipped IBM PC. If you just had the monochrome, it wouldn't quite work as well. But here's the code. All fits on one screen. You don't need to do all the crazy fancy color setups that you had to do on the TI machine. Things are a lot simpler. So we can see that the main difference is that here when we get down to line 215, all I do is say, all right, well, if I is 15, that means we've gone through the maximum iterations. I just change it to 1 because I know it's going to be a value between 1 and 15. So I just want to shift that to something between 0 and 14 and just take all those 15s and make them zeros. So that's how I managed to do that. And then I have at my disposal the locate instruction on BASIC. And as you can see here, I'm taking PY and adding 1 to it. and doubling px and adding 1 to that, because we're dealing with a 1-based system. So doing a locate 1 1 will put me in that upper left corner. And what I want to do is actually print out 2 spaces in a with a background color from the 16 color CGA palette. And that's what that color 0, I will do. So it takes that color value between 0 and 15. 0 is black. That's why I've moved that back to the beginning, so that when we go through the maximum iterations, we'll have black. And then we'll have the other colors 1 through 14. Those color indices will be able to make the background color. Now, some people are thinking, well, wait a second, isn't CGA 4-color? No, 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 no. CGA is not a 4-color graphics card. It is a 16-color graphics card. But when you're dealing in graphics mode, in like bitmap graphics mode, at the normal like full resolution, which would be like 320 by 200, which is the most common graphics resolution, that you were limited to for a specific 4-color palette, a subset of those 16 colors. But in text mode, you have access to all 16 colors on screen at once. And or there's even like these lower resolution graphics modes that you have access to on CGA that weren't terribly useful for games, but you could do 16 colors there as well, because it used up less video memory. And this doesn't use up a whole lot of video memory doing it this way, because it's character based. It's like effectively a tile map. So, but here our tiles are going to be 2 spaces in each. So we're dealing here with characters that aren't square like on a lot of these 8-bit machines. They're half as wide as they are tall. So 2 spaces together will give me a nice square bit of color. And it's going to be that background color based on the number of iterations. So let's go ahead and run it, and we'll get our stopwatch ready, and we will run and time it and see how fast we go. And you can see right away a lot faster than the TI. And because we have here an 80 character display, an 80 character width display, even doubling up those spaces, the 32 of these pixel plots, they don't take up much of the screen. But now here we're getting into more of the computationally complex parts of the plot, where we have more of these black pixels to get through. But there we go. We're getting through. We can kind of see here some of the artifacts of drawing these frames. So it looks a little janky maybe on the desktop recording, but it's going to come through here in the end. So we're just going to let this finish running here, although we're about to hit that midway point, and we're just over a minute right now. But look, we're going to go ahead and speed it up for the rest of it and get through this whole plot. So there we go. At 2 minutes and 51 seconds. So not too bad, but really sort of middle of the pack for those 8-bit computers that are coming out around the same time, and a lot of them for a lot cheaper. But again, it's still pretty much like the same basic that was just being rewritten for the 8088. So let's leave out of here, and then if we hit exit, we'll get back to Linux, and there we go. So yeah, with that PC, you definitely got something that was like faster than a Commodore 64, but not as fast as some of these other machines. So what we can do is bring up the cycles, and here we will take out that PC XT version, and we will save it now with the AT speed, and we're going to see how fast we're going now. So we got to do the same thing. We bring up DOSBox, and we got to remount that virtual floppy drive. And then we just bring up GW Basic as before. Oh, gotta be on that A drive. Can't forget that. All right, and then I can load up again man CGA. It's going to be the exact same code, but again, this is tokenized basic code. This is not machine code, and so I'm not really running it on a 286, but it's going to be something as fast as a 286 approximately. And so now let's see if we run this, how fast is it going to be? Oh yeah, a lot faster. So yeah, the just increasing that speed 4 times, we can see we still get some of those artifacts there where it doesn't quite render those spaces, the background colors fully. I don't know if that's something you would necessarily see on the real system, or if that's just a weird artifact of the way DOSBox works, because DOSBox, it's still trying to do things on a modern system and dealing with modern graphics frameworks and all that. So we'll see. We'll see how it goes. But we're heading to the end here real quick. There we go. 42 seconds. Not too shabby. All right. So yeah, by the time we had a 286 in the mid 80s, it became real apparent that these 16-bit computers are really far more capable. Not just the logistics of using them, it became just a much faster way of doing things. Even if you still didn't have quite as fancy graphics as you had on, say, a Commodore 64, you could get a lot more done with a PC. It was a much more useful machine. So now here's our final leaderboard. And we can see that IBM PC just really taking the cake, especially once we got to the last 16-bit IBM PC, which was that the PC AT 5170. And once we eventually getting past that, IBM would kind of go in a different way with their PS2 computer, and then the clone manufacturers eventually moved on, taking that AT sort of architecture and building that around 3D6 based machines. Like we saw that compact 3D6 was one of the main benchmarks there. And then we'll move on with the 46 and the Pentium machines, and then eventually we get to where we are today. But in terms of what IBM did with their architecture, their original 16-bit architecture, this is as good as it got. And 42 seconds, it's almost as fast as the Commander X16, which is also running at 8 megahertz, but with a 6.5 CO2. And again, it kind of shows you that how powerful that 6.5 CO2 is to do something like run BASIC compared to a 286. Now, we'll when we're going cycle for cycle, it does seem comparable, but again, we're dealing with basic code. We're not dealing with machine code. So things may get a bit different once we start getting into the actual machine code for the IBM PC and doing that 86 based assembly language, and getting right down to the registers and start doing some of the 16-bit math a lot more efficiently. But what we won't see is our friend the TI 99.4A in assembly language. There just seems to be no point in doing that. This is obviously going to be way, way underpowered compared to any other 16-bit computers. But we do have more coming up. We're going to continue this first round of the 16-bit Battle Royale with other 16-bit computers that came out in the 80s, like the Apple Macintosh and the Commodore Amiga, the Atari ST, and even seeing Apple again with the 2GS. We have all of these systems, each have something interesting to bring to the situation. And so the question is going to be, once we get through all of these, which one is going to be the fastest? Will these 68,000 based systems be more performative running BASIC? And then consequently with machine code. What about the 65 C816 that's running on that Apple II GS? That is a 16-bit version of that 65 CO2 on the Commander X16. In fact, the Commander X16 was at one point going to use that chip, but it ended up going back to just doing the straight up 8-bit design. Is that going to be comparable to a 286 or a 68,000? It's a very interesting question, and I hope that you're as interested to find out what the answer to that question is going to be as I am. And if you are one of those people, chances are you're going to like all the other content I have on my channel. So I would highly recommend going back and subscribing, and of course liking this channel, liking this video, and commenting and tell me what you think about this idea. What maybe I'm missing a few other 16-bit machines besides the ones I just mentioned. But if you want to go the step further and not just be satisfied with that free subscription on YouTube, you can help directly support my channel on Patreon. Or you can even click the join button here on YouTube if you don't want to do the Patreon thing. But on Patreon's really where the big community is. And these folks here get to see all my videos ad-free before they come out to the general public, and really make a big difference in terms of the direction that my channel goes, and providing a lot of that early feedback and being that sounding board for a lot of the ideas that I have in terms of the kind of great retro development content that folks want to see here on YouTube. All right? So I hope to see you again here soon, and until then, bye-bye.